In this video, we'll be taking up the Chapter 7 homework sheet. So for question 1, they're asking us to write each as a power of base 8. So the only one that's a little hard is 1c. As long as you know your powers of 8, this question will be okay. But for 1c, 32, if you want to express 32 as a base of 8, you need to be a little creative. So 8, the cube root of 8 is 2, and 2 to the power of 5 is 32. So that's why 8 to the power of 5 over 3 is exactly the same as 32. So as long as you know your powers of 2, 3, 4, 5, 6, 7, 8, 9, 10 for this unit, you should be okay with these kinds of questions. For question 2, it's a really nice question. You can actually change any number to a power of any other base, as long as the base is not 1 or negative values. So I changed it to a base of 8 for 2a using the relationship of inverses and powers being using the relationship that powers and logarithms are inverses of each other. Well, as long as the bases are the same, so I get an exponent of 1.441. I find it silly that the sheet wants you to round it to 3 decimal places because I would personally prefer the exact answer. But anyways, I think it's just practice for you to evaluate logarithms. And I did the same thing for 2b. For question 3, we're just solving an exponential equation, set the bases of the powers to be the same, and then you can equate the exponents. So 3a and 3b are about the same. Number 4, different ways to do it, but the way I chose to do it is break the power down, and then that will help me isolate for x. So use your grade 9 exponent laws, and then you can easily solve for x by changing it to logarithmic form. Question 5, let's see. Oh, basically you have another exponential equation that's very similar to question 4. The right side, the power on the right side is a little more complicated, but nonetheless, just use your grade 9 exponent laws and then rearrange. And they wanted me to round it to 2 decimal places, which I find very silly because exact answers are perfectly fine. Question 6a, we have a half-life situation. So they're asking me to solve the half-life given some information. So I solved the half-life to be about 82.2 hours. And then 6b is basically based on 6a. So knowing that the half-life is approximately 82.2 hours, you can solve for when 5 milligrams will be remaining from the 30 milligram sample. So it's about 212.6 hours. But without the half-life from a, you cannot do b. Okay, 7a and 7b, you basically have the quadratic equation from the exponential equation. Factor, solve, not much to say. Be careful, 2 to the power of x equals -1. You get no roots from that because 2 to the x must be greater than 0. For question 8, you're solving for the doubling time. And the doubling time is about 1.58 months. Yeah, t is the doubling time, and d is the doubling time, and t is the time that's passed, so about 1.58 months. And then once you have the doubling time, you can solve for the time it takes to reach a population of 10,000. Okay, I would argue that question 6 and 8 were very similar. It's just that one is dealing with half-life, and this one is dealing with exponential growth. Okay, so number 9, you want to use your logarithm laws to help you evaluate. So I use the quotient law of logarithms, power law, product law of logarithms to answer 9a and b. For question 10, we're expressing the expression as a single logarithm. So we can do so by using the power law of logarithms and the product law of logarithms. And don't forget to state your restrictions. For question 11, you're basically doing the opposite of question 10. So you're breaking apart that single logarithm and expressing it as a sum and difference of logarithms. Don't forget to use your power law of logarithms to simplify further. For question 12, The simplifying part should be pretty simple. It's the restriction part that's challenging. So you have to make sure the argument is positive. Now, in order to determine when the argument is positive, you're basically solving polynomial inequalities like you did in chapter 2. So when is x squared minus 4x minus 12 greater than 0? You can solve that polynomial inequality. When is 3x minus 18? Same thing. So I didn't show all the work, but I basically factored and I graphed it in my head. But if you can't do that, you can graph it out on a separate piece of paper. So I need to find out when both of these arguments are simultaneously positive. So I look at the two number lines and I look when are they both highlighted. And in this case, it's when x is greater than 6. So that's my restriction on this expression. For B, the restriction is when x is greater than 3. For question 13, we're basically solving we're solving logarithmic equations. So with logarithmic equations, don't forget to state your restrictions. So change it to exponential form for 13a, and you basically solve for x in a few steps. For 13b, you have to rearrange and use the product law of logarithms. And when you solve, don't forget to check whether you have extraneous roots or not. And in this case, you actually do have an extraneous root, -3. Question 14. Question 14 and 13b are very much the same, but for 14 it doesn't end up being factorable, so you have to use your quadratic formula, and you end up with another extraneous root. For question 15, they basically give you a formula, and you just have to use a formula and solve for a variable. So if they give me the temperature, I can solve for the time, and if I am given the time, then I can solve for the temperature. You just have to play with your logarithms. So once you rearrange, exponential form, and then you can easily solve for t. Okay, so that's it for chapter 7 review.